Hello students, in the previous lecture we have talked about differential scanning calorimetry, which is a thermal methods of analysis. Today we will talk about another method, which is thermomechanical analysis. In the lecture we will talk about instrumentation for TMA, that is thermal mechanical analysis or thermomechanical analysis, probes used in TMA, calibration, linear thermal expansion, glass transition temperature and the applications of TMA. The basis of TMA is the change in the dimensions of a sample as a function of temperature. A simple way of looking at TMA is as a very sensitive micrometer. TMA is believed to have developed from hardness or penetration tests and was used on polymers in the year 1948. Subsequently, it has developed into a powerful tool in the analytical laboratory. TMA measurements record changes caused by changes in the free volume of a polymer. Thermomechanical analysis is a technique used in thermal analysis. It is a branch of material science which studies the properties of material as they change with temperature. Thermomechanical analysis is a sub-discipline of thermomechanometry. In short, we call it as TM. TMA is the study of the relationship between a sample's length, or you can say volume, and its temperature. TMA, or sometime called as dilatometry, is used to determine the linear thermal expansion of a solid as a function of temperature. Unlike the classical methods in which the experimental setup is kept as free of forces as possible, in thermomechanical analysis a constant, usually a small load, acts on the specimen. For example, this is a block diagram of TMA. Here you can see that we have a force generator and we apply a force on the sample, which is here, and you can see the red one is furnace and this is a sample cylinder. You can see here the probe, a thermocouple to monitor the temperature. So, with the help of this force generator, we apply some fixed force, and with the help of this furnace, we apply temperature and monitor with the help of thermocouple. The sample is inserted into the furnace and is touched by the probe, which is connected with the length detector and the force generator. The thermocouple for temperature measurement is located near the sample. The sample temperature is changed in the furnace by applying the force onto the sample from the force generator via a probe. The sample deformation such as thermal expansion and softening with changing temperature is measured as the probe displacement by the length detector. Linear variable differential transformer, that is LVDT, is used for length detection sensor. Here we are simply considering the sample O1 and this is the temperature sensor which we have seen. This is our probe, this is the position sensor, we can adjust the position, this is the drive shaft, this is the force motor which is used for applying the force. This is a typical instrument used in TMA. Here you can see we have a furnace as we have seen in the block diagram, sample carrier system, thermostatic controlled support, this is displacement transducer, and we have a force sensor, then vacuum tight housing, and this is how does it look like from the outside. Now, if we see here, this is actually the load or the force generator, then we have a quartz glass probe which passes through this induced position sensor. We have a thermocouple near the sample and this is our furnace or heater. So, this is apparatus which is above the specimen. Now, on the right hand side you can see apparatus which is beneath the specimen is the quartz glass tube. We have a sample here and then the sample holder. Different shapes of probes are used in TMA. The probe's shape differ so as to accommodate various specimen geometries which may be films, fibers, varying cross sections and specific experimental goals like measurement of expansion, behavior or of glass transition temperature. Here you can see the first one is a normal probe, from the bottom you can see it is flat. Second, this is macro probe where we can see that at the bottom it is slightly bigger in comparison to the flat probe. The third one, penetration probe, here you can see that we have a small portion which is coming out of this probe and it is used for penetration experiments. And fourth is the setup for films or fibers in the tensile mode. The choice of probe depends on the geometry of the specimen. For determining the linear thermal expansion, it is preferable to use probes with relatively large contact areas. Where the specimen is large enough, a macro probe with a contact area of approximately 28 millimeter square is used. For a smaller specimen, for example, with an edge length less than 6 millimeter, a normal probe with a contact area of approximately 5 millimeter square is suitable. Penetration probes with a small contact area of just about 0.8 millimeter square are suitable for determining the glass transition temperature. Special holders allow thin films and fibers to be measured. For this, the specimen is held between two clamps and then suspended in the measuring device. Now, before the use of the instrument, we have to calibrate the TMA instrument. Here you can see this is on x axis we are having temperature and on y axis we have length change in micrometer. So, for calibration, if we are using indium, tin and bismuth, we can see here that at a heating rate of 5 degrees Celsius per minute and force 1 Newton and in static air atmosphere, we must get a curve in which we can see that the temperature up to about 150 degree, the length remains constant. Then there is a sharp decrease and then again the length becomes constant. Then around 230 degrees we see a change in length and again this becomes more or less constant, and then again at 275 we see a sharp change in length. Now, these three steps clearly indicate that indium, tin and bismuth, they are showing the change in length with increase in temperature. So, if we get these three sharp steps or these three sharp changes in length versus temperature curve corresponding to 156.6, 232 degree and 271.4 degree, we can conclude that our instrument is properly calibrated. Now, for further calibration, we can use thermal expansion of 5 mm high aluminum cylinder, which is used to check the length calibration of TMA. Here the heating rate is 10 degrees Celsius per minute under static nitrogen atmosphere with a load of 0.01 Newton. You can see here that temperature and length change gives almost a linear relation, and the value of alpha was found as 24 into 10 raised to the power minus 6 per degree Celsius. Now, for glass transition temperature, we have to use calibration in which, for example, we are taking printed circuit board which is 1 millimeter thick, and we can see that with change in length with temperature gives a break in the curve. Initially, this change is linear, and at around 112 degree we see another slope of the curve, and both these curves show an interaction around 112 degree C. The value of alpha in the first case is 50 into 10 raised to the power minus 6, whereas in the second case it is 150 into 10 raised to the power minus 6 per degree Celsius. Now, this is the plot of the change in length of a sample of a silicon gum rubber at different applied forces. You can see here that we have applied a force of 0 gram, 1 gram and 5 gram. So, if we use 0 gram, you can see that with increase in temperature the length increases, and at around minus 70 degrees the change becomes more rapid, whereas at 1 gram we get the results in which there is decrease in length followed by the constant nature of the curve, and then again at around minus 20 degree it shows a decreasing trend. Whereas, if the applied force is 5 gram, you can see here that the curve at around minus 70 degree show a sharp decrease in nature. Now, let us come to procedure and influential factors in TMA. The stages involved in a TMA measurement are as follows. The first one, prepare plane parallel specimens, measure initial length, that is L0, load the specimen in the instrument, choose applied load, choose suitable experimental parameters. You can see here that the influential factors are specimen preparation, stress, which is load, then the geometry of the specimen, the starting temperature, then the heating rate, and finally, the type of load, that is the shape of probe which we are using. Here we are showing you a plot between temperature and change of length for evaluation of mean delta T and differential alpha T coefficients of linear thermal expansion. Here we can see that the curve between temperature and change of length is almost linear between T0 and T1, and then it shows a bend, and up to about T2 you can see that this increase is not linear. Now, the change in the slope, that is at T1, and the change in slope at T2, the change in temperature is called as delta T, and the change in length is called as delta L, and we can divide it by the original length, that is L0. Alpha T is differential coefficient of linear thermal expansion. Alpha bar is represented as mean coefficient of delta T linear thermal expansion. Delta L by L0 is change of length, delta T is change of temperature. Tangent at a temperature T2 gives slope at one point. Slope over a temperature range is delta T, and change of length over a temperature range expressed in terms of initial length is L0, and difference between the two temperatures is represented as T2 minus T1. The coefficient of linear thermal expansion may be recorded as the mean alpha delta T or differential alpha T. The mean coefficient of linear thermal expansion alpha is derived as follows. Here we can see alpha bar delta T is equal to L by L0 multiplied by L2 minus L1 divided by T2 minus T1, and this is equal to L by L0 multiplied by delta L divided by delta T. Alpha delta T is an experimental value that varies in each case over the individual temperature measurement range. Mean coefficient of linear thermal expansion is alpha delta T. Differential coefficient of linear thermal expansion is represented as alpha T. The differential or local coefficient of linear thermal expansion alpha T is derived as follows, where alpha T is equal to L by L0 multiplied by dL divided by dt. The values may assume the dimensions 10 raised to the power minus 6 per degree Celsius, or this may be in Kelvin. Then comes glass transition temperature. At the glass transition, many physical properties of amorphous plastics or of the amorphous domains of semi-crystalline thermoplastics undergo stepwise changes in several orders of magnitude. The same applies to their coefficient of linear thermal expansion. The figure shows how loading affects the linear expansion and the differential coefficient of linear expansion for plastics at the glass transition temperature. Here you can see that temperature on x axis, expansion on y axis. You can see here that initially with increase in temperature, the curve gives almost a straight line, and then at glass transition temperature this shows a break, and then there is sudden rise in expansion. From this curve, the value of T g was calculated close to 110 degree Celsius. In glass transition temperature, the first heating phase yields information about the actual state of the specimen, including its thermal and mechanical history. When thermoplastics soften, especially above the glass transition, orientations and stresses may relax, as a result of which post crystallization and recrystallization processes may occur. To determine the coefficient of expansion as a material characteristic, the material must not undergo irreversible changes such as post crystallization, post polymerization, relaxation of orientation, or internal stress and so forth during a second heating phase that has followed controlled cooling. Now, here we see effect of chemical structure. Now, changes in the linear coefficient of expansion alpha of linear aromatic polyesters with increasing the methylene content raises the thermal coefficient of expansions and lower the T g of the system. Here you can see we have 3 curves, and with increasing methylene content we can see that the value of alpha also changes. Here let us study effect of plasticizers in TMA. If we plot change in length with temperature, and here the first curve shows the sample is unplasticized. Now, with increase in plasticizers to 5%, 10%, 20% and 40%, we can see that the nature of the curve changes, and now we see that the break in the curve shifts to lower potentials. For example, when we are using 40%, you can see that the break in the curve is around 0 degrees. TMA applications are in many ways the simplest of the thermal techniques. TMA measures the change in the size or position of the sample. However, it is also important in supplying information need to design and process everything from chips to food products to engines. Because of the sensitivity of modern TMA, it is often used to measure T g that are difficult to obtain by DSC. For example, those of highly cross-linked thermosets. TMA allows the calculation of the thermal expansivity. Determine coefficient of thermal expansion of material. Identify T g and Tm of several materials. Measure materials heat deflection temperature known as HDT. It is used for composite delamination temperature. Epoxy system, we use TMA, which accurately measures dimensional changes in a material when the material is subjected to a temperature program. For a cured epoxy system, the output from TMA will be the coefficient of thermal expansion and glass transition temperature. The CTE of the epoxy is a very important parameter because a fine gold wire is embedded in the epoxy compound and a high CTE may cause the wire to break prematurely when the electronic component is subjected to repeated temperature cycles. The deflection point between the different coefficient of thermal expansion can be defined as the glass transition temperature. TMA is also used to determine the softening point of plastic components and the melting point of solder. To summarize, we have learned today about thermal mechanical analysis, intrinsic properties, TG, alpha and probe displacement, its viscoelastic properties, Young's modulus, then creep, stress relaxation, tensile properties, viscosity, polymers and copolymers. Then we have learned its application in polymer blends. Polymer morphology. In process properties, we use this technique for cure and cross linking, polymerization, solvent effects, foaming, phase behavior, flow modeling, crystallization, Drolling effects, viscosity, mold stability, and in product properties we use it for carbonaceous materials, ceramics and coatings, construction material, composites, dental waxes, elastomers, metals, pharmaceuticals, textile, plastics. We must remember that intrinsic properties arise from the chemical and physical structure of a material and can be measured with precision, whereas the process properties simply reflect the intrinsic properties in a dynamic environment. Now, this finishes the unit on thermal analysis, in which we have learned various thermal methods of analysis, including DTA, TGA, differential scanning calorimetry and thermal mechanical analysis.